Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a video in the series of graphs of polar equations for a trigonometry or pre-calculus student. And we've just likely, if you're watching my videos, gone through graphing a bunch of polar curves. But I didn't bother really naming those polar curves because that gets in the way. What I really wanted to do was just show you a method for graphing polar curves. Now I'm going to go ahead and give you the names and also the patterns. So the first group, and by the way, there's no real reason to name every single polar curve, but the important ones are the ones that I'm naming here. The first group I'm going to name are the cardioids, and these are polar curves from derived from the equations r equals a plus or minus a cosine of theta, or r equals a plus or minus a sine of theta. Notice these a's are the same. So in size or in magnitude, those a's will be the same. All right. They don't have to be the same sign though. I should say that. So it could be, for example, r is equal to -3 plus 3 sine of theta or something like that. That's perfectly fine. But in magnitude, they are the same size. This one on the right-hand side is the sine, and the one on the left-hand side is associated with the cosine. And specifically the positive cosine and the positive sine. If it was a negative sign, it would be upside down. It would look something like this. Terrible drawing as it may seem. I'm not going to give all the other details about this because I think that's really memorizable. Main thing is you can find out what all of these points are very quickly by saying, well, what if I face an angle of pi over 2? What's the value? And so on and so forth. You can actually see, for example, with r of theta here, if you decided to face an angle of pi over 2, you would get a plus or minus a times the sine of pi over 2 is 1. So a plus or minus a. Just depends. So in this case, a happened to have been 3. So it's 3 plus 3. Anyway, those you could derive very, very quickly. So I don't really recommend you memorize that. Instead, just memorize the forms of these. That if the coefficients of the cosine or the sine and the constant, if they match in magnitude, you will get a cardioid. And you don't even need to memorize that if you could just draw it. Another common style of polar graph is the limacon. There's actually two of them, the two limacons. One we call just a regular limacon. That's what this guy is right here. We saw these in our graphing videos for the a plus or minus b cosine or sine. These occur if the constant is greater in magnitude than the coefficient of the trig function. The constant is greater magnitude than the coefficient of the trig function. And I recommend that you spend some time really trying to figure out why. Actually, I'll showcase why in a few minutes here. I'll bring up Desmos and we'll actually explore these. But these are limacons. And then the next kind are called limacons with inner loops. And these are the ones that you saw, you had little inner loops going on. And oops, the function here was supposed to be a b, and this is supposed to be a b as well. So if you're one of my students, you probably already have that fixed. But this is where the coefficient of the trig function is greater than the constant in magnitude. And finally, we had the roses. And you had for example, the n leaf roses. So if n is even, then n equals number of leaves. no, 2n is equal to number of leaves. Okay, so in this case, what you're looking at are the sine and the cosine of 2 thetas. And if n is odd, then you have n is odd implies n equals number of leaves. And again, this just takes time to kind of fiddle with, but let's go ahead and see all this in Desmos, because just seeing this like this really doesn't help out. So let's go to Desmos and play around. So here I am in Desmos. Notice to the left-hand side here, we have a plus b sine of theta. And we're going to play with a and b. What you see right now is a and b are the same. And what happens is that as theta gets large, if a and b are the same numbers, I shouldn't say as theta gets large, I should just say this. If a and b are the same numbers, remember, sine fluctuates between -1 and 1. So if a and b are the same, let me just say it's a and a here, then there is a chance that they will cancel because sine will be a -1. So you get a minus a and they'll cancel. And that's how you get back to the origin, the pole here. That's why it drags in, is because they have the ability to cancel out. They only cancel out when sine of theta becomes -1, which is at 3 pi over 2. Now, what if instead of a and b being the same, you had b greater? So notice I'm allowed b to be greater there, and we get that inner loop, right? In fact, I'll zoom out so you can really see it happen. As b gets really big, it's an inner loop. It'll always be an inner loop. It won't ever exceed or go outside the outer ring. But what makes that difference? Why does it do that? Well, if you can imagine it, we're saying that a is 1 and b is 2. Well, at some point when you're drawing, specifically when the sign starts to go negative, you're going to start subtracting something from that 1, and that something can be all the way up to 2. So you could subtract all the way up to 2. So you're going to start throwing rocks behind you, and that's where we get this inner loop here. That's where we get this loop back. So not only can it become 0, and maybe I should plot a point here. There we go. So not only is it going to, like, for example, right now, we're almost facing an angle of pi over 2. Well, sine at pi over 2 is 1. So we're 1 plus 2, which is 3. That makes sense. But eventually, sine will get to a point that'll start to go negative, and it'll start subtracting. In fact, that's its sine's getting smaller and smaller and smaller, and it eventually starts subtracting once we get to pi. And when you get to pi, it'll start subtracting 1 minus a number. And at some point, it'll say 1 minus 1, and we're back to our feet. And then it starts to go really negative. 1 minus 1.5, 1 minus 1.9, 1 minus 2. That happens right there. And then it starts to grow, and it goes positive again. So anyhow, that loop comes from the fact that you'll subtract off more than 1 at some point. Now what happens if you switch it up? So I'm going to bring this back to A, and I'll bring this back to B. And instead of A being 1 and B being 2, we'll do A being 2 and B being 1. And notice that look, we lost the inner loop, right? We had a cardioid when A and B were the same, and a loop when A was less than B. But notice when you pull that out, it gets a little flatter at the bottom. It's like a flat tire almost. And the reason why it never gets to the origin is because you're dealing with something that looks like this. 2 plus 1 sine of theta. Remember, sine of theta ranges between -1 and 1. So 2 plus 1 or minus 1, that'll never become 0. So as you rotate around, it'll never shrink back to 0. It just won't. And so that's why the limacon never goes back to 0 or back to the pole. Anyhow, you can play around with something like this. You can just go to Desmos and type in your own value here. It'll ask you if you want to set a number line, and you could totally do this. This is actually pretty informative, I think. You can kind of get the patterns of when things occur. All right. That's all I really wanted to say here. If you want to fiddle with n-leaved roses, you can just make this n and add a slider to that. And the slider, just make sure you go from 1 to, let's say, it doesn't really matter, 5. We'll step by 1. And when you do that, I'll zoom in. When n is 2, you get 4 leaves. When n is 3, you get 3 leaves. When n is 4, you get 8 leaves. And when n is 5, you get 5 leaves. So you can fiddle around that with that if you want. I think that it's kind of neat to see how these are developed. So go ahead and fiddle around with those. If you're one of my students, do not worry. I don't have you graph one of these n-leaved roses on an exam or something like that. However, in homeworks, you should practice that. In calculus, you'll have to be able to graph these. These do end up being graphed quite often in calculus. So that's something that when I say calculus, I mean Calc 2, something you have to get used to.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.